In the Why CTLE video, we briefly mentioned why you need the active CTLE implicitly, but there has been a lot of feedback about the active CTLE discussion in the circuit image YouTube channel. Therefore, let's go through why active CTLE in high-speed SerDes explicitly here. We've known there are two types of CTLEs from the Why CTLE video. One is called passive CTLE and the other is called active CTLE. But how do we identify those two types from the AC response image here? Think about the gain images for 5 seconds. Correct. Looking at the maxima or peak gain around the next ray. If the AC gain at the next ray is less than a magnitude of 1 or 0 dB, we call it a passive CTLE, since the high-pass response without a signal gain was generated through a few passive elements. On the other hand, you should catch if the AC gain at the next ray is greater than a magnitude of 1 or 0 dB, we call it an active CTLE, since the high-pass response to signal amplifications was generated through a few active devices. After knowing the AC gain at the next ray defines the passive or active CTLE, perhaps we could ask an equivalent question of why active CTLE to be why a CTLE with an AC gain. Any idea? Think about the swing images at the next ray for 5 seconds. Great. The swing at the next ray of a data bit stream is the clock pattern called the 1010 pattern, D10.2 pattern, etc. First of all, let's look at the link of a high channel loss in order to give you some idea of what the swing image looks like. We not only provide the 1000 mV at the TX output, but also show you a high channel loss of up to 30 dB at next ray. Therefore, you should imagine only 31.6 mV at the RX input after the 30 dB loss. The AC gain requirement would translate to if the 31.6 mV is good enough. Think about the image of the RX sampler's input sensitivity for 5 seconds. Bingo! The input sensitivity image of the 10 gigabit per second sampler shows that the clock to Q delay is 65 picoseconds, with the 50 mV input and the clock to Q delay will violate the 10 gigabit per second timing for an input swing of 31.6 mV. Therefore, if your SerDes is targeting a data rate beyond 10 gigabit per second at the loss greater than 30 dB, you must apply the active CTLE to provide enough AC gain, at least 10 dB, to boost the input swing of the sampler around 100 mV. This will be the first necessary case of an active CTLE. On the other hand, if the channel loss is not big, do you still need an active CTLE? Think about the swing images and input sensitivity image of the sampler in a series for 5 seconds. Bingo! If we keep the 1000 mV at the TX output with a low channel loss of down to 10 dB at the next ray, there is a 316 mV at the RX input after the 10 dB loss. For your last image of the RX sampler's input sensitivity, you should claim that the 316 mV should be good enough for a data rate not only up to 10 gigabit per second, but also 20 gigabit per second. So we definitely don't need any CTLE gain from the active CTLE. Is that true? Think about the power images of a C-Link for 5 seconds. Correct. As we mentioned in the Why CTLE video briefly, an active CTLE is more power efficient than the TX output driver due to the TX output low impedance in a 50 ohm. But in the active CTLE, as long as the resistance is low enough without introducing too much thermal noise, the resistance should be still high enough up to 200 ohm range to have the same output swing as the TX output, but 4x less current or power. The power budget image of a link shows you that the 1000 mV swing may require 20 mA from a CML type TX driver, even though the passive CTLE is good enough to keep a 300 mV swing at the sampler input and meet its input sensitivity and output timing. But we could reduce the current of the CML type TX driver down to 4 mA, which needs an active CTLE in a CML type with an extra 4 mA current budget at Rx, such that the total current of the link is only 8 mA. From the power budget image, you should realize the active CTLE would actually save the holding power more than half, which is quite a bit. In addition to the power budget at the link, do you see any power saving image in a realistic application? Good. Sometimes the source of the link could be a mobile device, which requires a very low power mode in the TX driver. Therefore, minimizing the TX swing under low cable loss by pushing the input swing of the sampler back to enough level by using an active CTLE and a sync device not having a low power requirement makes more sense. After we know the active CTLE can help the power optimization or reduction, what's the remaining advantages that the active CTLE can provide? Think about the signal to noise ratio SNR image from the AC images for 5 seconds. Bingo! To equalize a 30 dB channel loss, the peaking gain, which is the gain at the next ray minus the DC gain, should be 30 dB, no matter the active CTLE or the passive CTLE. The only difference is the gains at the both DC and Nyquist ray of the passive CTLE is all shift up by 6 dB, which is a factor of 2. Therefore, after perfect equalization, you can see that both long run pattern and D10.2 pattern at the passive CTLE output are still 25 mV. But both the long run pattern and D10.2 pattern at the active CTLE output is 50 mV. The reason the active CTLE could have twice the I high of the passive CTLE is owing to its 60 dB gain at the next ray, such that the D10.2 pattern is multiplied by 2 to be 50 mV. Also, the active CTLE's DC gain is minus 24 dB, which has half the emphasis or degenerated from 800 mV to 50 mV. Therefore, the SNR of the active CTLE in this case would be twice of the passive CTLE, assuming the noise level is similar in a good design of a noise optimization, but the swing is twice. Here is the summarized image of why we need an active CTLE in high-speed SerDes. For high channel loss like 30 dB at the next ray, the input swing of the CTLE could be only 30 mV, even though the TX output swing is 1000 mV. In addition, as a very high-speed SerDes, the sampler or comparator may need a big enough input swing to meet the following digital timing due to its poor input sensitivity at such a high speed above 10 gigabit per second. Therefore, we may need the active CTLE to enhance the sampler's input level and mitigate its input sensitivity impairments as well. On the other hand, if channel loss is low enough, like 10 dB at the next rate. It's not necessary to burn lots of power at the TX driver due to its low output impedance. On the other hand, we should program the TX swing smaller to reduce the power and enhance the input swing of the sampler by active CTLE under a bit more power owing to its higher output impedance than the TX driver's one. Another necessary usage would be the source device TX driver could be the mobile or low power requirement devices such that the CTLE must provide the AC gain. The last critical performance is the bit error rate or SNR. With an active CTLE, the equalize are high for both the long run pattern and the 10.2 pattern would be bigger than the one of the passive CTLE, assuming a similar noise level with a careful design in noise consideration. Lastly, the active CTLE provides a signal gain, which helps improve the sampler's input sensitivity, reduce the power from the TX driver or source mobile devices over the whole link, and reduce the bit error rate by increasing the SNR. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may benefit from it.